What's going on, guys? Sam Prentice here, and today I've been asked to pop over to the E3D offices just outside of Oxford in the UK to check out one of their new products. Let's get straight into this one. Right then, guys, what is going on? Mike and Sam, how's it going? Wow, look at this. Guys, what are we here to see today?
Here to look at this.
Oh, wow, what is this? Is this that? Okay, so what is it, first and foremost?
So this is Roto, which is our latest extrusion system, and we're super pumped about it. There's loads of awesome features which we want to dive into today. But I think the thing you were looking at, that was a 3D printed heatsink.
Yeah, so 3D printed metal.
Yep.
That is beautiful, by the way.
Thank you.
That is incredible. So who's this for?
So Roto's really for anybody in terms of looking to improve the performance of their extrusion system on their machine. We've got loads of features on there for usability in the same way that with the Revo ecosystem, we've looked at making everything as user-friendly as possible. So we've got things like locking idlers, integrated filament sensors, heatsink temperature on there. I'm sure we'll go into some detail on that later. Important to have good level of usability, but at the same time, we want the print quality that everyone expects out of E3D, while also optimizing it, making it smaller so that people can incorporate it on faster, higher acceleration machines. It's also for anyone that's looking to perhaps unlock some additional print speed. They're worried that at the moment their extrusion system's pretty heavy and moving that around is causing there to be a speed limit on their printer. So hopefully it appeals to people with older machines who are wanting to upgrade and unlock some new performance, breathe some new life into them, but also modern machines that are looking to design around a small, lightweight package. So the key design goal for Roto was to get the performance that you need at the same time as having no unnecessary bulk and then maintaining that usability and quality that you'd expect out of E3D.
So guys, what are we going to do today?
We're going to run through some tests, starting with a volumetric flow rate test. There's quite a few different models available for doing this, but we're going to run through what we do here at E3D. But not only that, we're going to compare it directly to Hemera. So what we're going to do is we're going to show that with a Roto and with a Hemera, you can get the same volumetric flow with a given nozzle and material and hot end combination. Then we're going to run into all the other aspects, because there's no point being able to print fast if you have poor print quality. So we're going to then compare the print quality from Roto to some other machines that you will see commonly on the market.
We're trying to optimize the design for the majority of our users, and for us it's kind of a balance between what features we choose to integrate versus what the knock-ons might be. So for example, there are certain things that you might add, but they might add a load more cost for somebody, or it might make the system heavier, which is then a detriment in another way. So what we've done is try to create the optimum solution as we think is appropriate for the majority of users. Just to give you some sense of scale of the amount of work that went into the development, I think we've got about 230 gigabytes of log data on our primary kind of force and load logging equipment, where we've done loads of quantifying and testing with Roto. Originally, when we started, it's now using injection molded components for the gears and the gearbox assembly. But before we committed to tooling that up, we used some machined prototypes. And I think we logged over 4,000 hours of print testing before we even tooled up the injection molds, which is about 24 weeks of continuous printing.
Yeah, I don't think, I think most people probably don't quite realise how much time and effort goes into actually launching a product like this. That's absolutely incredible.
Using a load cell, it is possible to log extrusion force against flow rate for a given system. This data shows the extrusion force against flow rate for Prusament Jet Black PLA printed through a standard 0.6mm brass Revo nozzle using a 60-watt heater core. It is important that this data be gathered with an extrusion system that has a headroom in extrusion force output to ensure that it is not a restriction on the system, and that the data covers the full range of flow rates for the given nozzle hot end material combination. As you can see, initially there's a relatively low increase in force requirement at low flow rates, then eventually there's a sharper increase in the force required up to the point of failure. This point is actually not, however, the maximum usable flow rate with this combination of nozzle, hot end and material. The actual maximum usable flow rate is here. Beyond this point, you start to see artifacts in the extrudate. You want some headroom of extrusion force above this point to account for things such as filament drag, which could increase the load required on the system in a given application. However, you do not need to be able to output the peak force on this graph, as this is not a usable flow rate. If we then plot another curve, this time for a standard 0.8mm brass Revo nozzle, with the maximum usable flow rate being here, as expected, the maximum usable flow rate is higher than with the 0.6mm nozzle. Focusing in on these points of maximum usable flow rate, we can begin to create a cloud of data for the extrusion force requirements. If we take this approach for a range of setups, we're able to generate a cloud of data points containing the extrusion requirements for various hot end nozzle material combinations. We can now use this cloud of data to establish force requirements for an extruder to ensure that it will not be the limiting factor in a system. This is where Hemera sits for its force output against flow rate. As you can see, Hemera always has enough extrusion force output to be able to extrude at the maximum usable flow rate for each given nozzle hot end material combination. However, it also has a large amount of headroom, meaning it's not as optimized as it could be. On Hemera XS, E3D reduced the size of the motor, and as a consequence the force output comes down, as you can see here. However, there is still significant headroom above the requirements. This is the output curve for the Roto extruder. It has a high enough extrusion force output to be able to print at the maximum usable flow rate of these nozzle hot end material combinations, but it isn't carrying around unnecessary headroom. This has an added benefit that if the force were to rise above the force requirements for normal printing, such as if there was a tangle in the filament spool, for example, the extruder motor will stall. An optimized gear ratio shifts to a stalling failure mode rather than shearing the filament. While I was with E3D working with the tool changer, I actually asked them to show me this. It's easy to replicate by trying to extrude at a higher flow rate than the setup you have is capable of, and you don't have to wait long to see it. The noise you can hear right now is the extruder motor stalling.
So as long as you have enough force, is that not the end of the story? Well, as it turns out, no. In order to make the best product they could, E3D also wanted to bring the mass down as much as possible. So, well, we asked them about that. So Mike, why is mass bad?
So the lower you can get the mass of your kind of tool head carriage, the further you can push the accelerations of your print head as it's moving around on the machine. And that means you can ultimately move it faster. So as long as that's not your bottleneck, you can then push the print speed that you can achieve.
Big question. A weighty question, in fact. How heavy is it?
So the whole Roto extruder comes in at 140 grams, which, to put that into perspective for someone who's maybe familiar with 3D printing, it's about half the weight of an X-axis motor, like a normal NEMA 17 motor. Your entire extruder is the same weight as half of that.
Gotcha.
So one of the things that we chose to do is maintain the philosophy we had with Hemera, where we've got an integrated heatsink design. So you'll notice it's different to a lot of other extruders where you'll have an extruder at the top, you'll then need a separate heatsink with a fan below, and then your hot end. And that helps us keep a shortened filament path, which is good for print quality, but it also helps us keep the mass down.
So Sam, we've got the V-Minion by Rat Rig, we've got a Roto extruder and a Revo hot end. What should we be expecting here?
Some fast moves. So because we have really taken out all of the mass that we can from the extruder and extrusion system, it means we're being able to push the accelerations and the movement speeds.
Okay, well you hold on to the printer, yeah. I'll grip the table, and we'll hope for the best. Wow. Okay, so what sort of speeds were we getting to there?
So the accelerations were 40,000 milliliters per second squared.
Yep.
And the travel speeds were 1.5 meters per second.
My God, but we're not going to be printing at that speed, surely?
Not necessarily. I mean, that all depends on your track width, your layer heights, and what volumetric flow you can get from your system. But there is also a surprising amount of printing that isn't material deposition, it's just movement. Sure. So you're needing to move from one area of your print to the other. So the faster you can do that, one, the quicker you print, but two, your things like stringing are much improved if you can just zip to one part of the print.
I love that. That's amazing. Brilliant.
So this one is actually a 15.5 millimeter long NEMA 14 round, which isn't a standard offering. They go from 13.5 to 18.5. We looked at the 13.5, but that really just didn't have enough oomph to really get us going with this project. So we were literally looking at the 18.5, but as we were on about earlier, we just didn't want to carry around that unnecessary bulk. So we worked with a motor manufacturer who developed this motor to this custom sizing for this project.
So Sam, how do you measure volumetric flow rate?
So to get to the final output numbers for a nozzle material combination, we use these print tests.
Sure.
So they have a few features on them so that you can look at different aspects. You have overhangs, which you can see here, so that you can look at part cooling. We also have these tight curves. Both the overhangs and the tight curves also check layer adhesion. If your motion system is zipping around a corner, material isn't coming out molten enough to stick to the layer below, it won't adhere on top of each other, they'll be offset. And then you'll get this like bowing effect that you can see on some of these prints. Additionally, there's an extremely long section of track that is continuous, so there's no sharp moves, which means that your motion system can stay at a constant flow rate. So what you're trying to do there is empty the melt zone of your nozzle. So if you set off a test going and the material is already molten, you can go for a small amount of time faster than you could if you're in continuous printing. That's how we ended up with this model.
That's insane. That's brilliant. Okay, so we've got two different prints here. What are they?
In one of your hands, which one is it? This one, we have a Roto print, and on this one, we have a Hemera. Now, these are printed on the same tool changer, so the same motion system. They both are using a 0.6 standard flow nozzle with Prusament PLA black. It's worth noting that it was the same nozzle that we took out and we put into the extruder, and the filament moved along with it, so it's as close as we can get it to being the same. And what we're trying to highlight here is that with the Hemera one, as you go up in these layers, you're increasing the flow rate. So it starts off at 12, it then goes to 13, and then 14, and then on the 15 millimeters cubed per second, you start to get this rippling artifact.
Yeah.
Now that is from cold extrusion, where you're getting like pulsation of cold and hot, cold and hot. And so the usable flow rate of this is 14 with a Hemera. And what we wanted to show is that if you take a Roto, the same nozzle, the same filament on the same motion system, you get 12, 13, 14, and then again on the 15, you get the same rippling artifact. So you can get the same flow rate between the two.
So Mike, we've got some similar tests here. What are we testing for here?
So what we wanted to show to everybody is that if you take the same setup with the same Hemera and Roto on the same tool changer, and if all you change is the filament, this time looking for one that's got additives in it to make it a higher flow PLA, then you unlock additional flow rate performance from your system, but that performance is the same for a Roto and for a Hemera. So on both of these, we're using 3D filaments PLA X cubed, and as you can see from these, we now go 14, 15, 16, 17, 18 millimeters cubed. And that's the same on both prints, with them both kind of failing at the same point.
So with the ideal mix then of extruder and filament, we are essentially unlocking speed.
Yes. And what we'll eventually now be able to demonstrate is that if we were to change to a high flow revo nozzle, so next thing we'll look at is a 0.6 high flow revo nozzle, we'll see that the performance increases again. Or if we move to a material that's biased towards like flowing more, so PETG as opposed to PLA, we unlock even more performance. And then if we were to upgrade our nozzle size to, for example, a 0.8 high flow nozzle, we unlock even more flow rate performance. It's all about the combination of the extruder, the hot end, the nozzle size, and the material.
If we go back to Prusament Jet Black PLA, but change from a standard 0.6mm Revo nozzle to a high flow 0.6mm Revo nozzle, we unlock additional flow rate capability. This Roto flow rate test shows that in these conditions, the limit increases to 25 millimeters cubed per second. Keeping the extrusion system consistent, but changing the PLA for some Prusament Jet Black PTG, a material which naturally flows more, we can unlock additional flow rate again, with this print test showing that the maximum limit is now 32 millimeters cubed per second. Finally, by switching to a 0.8mm high flow Revo nozzle, the flow rate limit increases again. This test shows that the maximum flow rate is 37 millimeters cubed per second.
So Mike, how do you validate print performance?
So after just general flow rate testing, obviously the main thing really is the actual print quality that we're getting off the system. We don't just have like one test print for that. We've actually got hundreds that we run throughout development. There's a few examples here that we can show off. So we've got an E3D buggy and also our Rory the Lion mascot, which we've printed off in with a Roto on that V-Minion, but also on a couple of other kind of common popular machines on the market right now. And when you take a look at them, you can see that on some of these others, we're getting extrusion artifacts in the surface, whereas when you look at the quality off the Roto, the precise metering of the extrusion ultimately means that we're getting a nicer quality print. And just for reference, these are all printed at about the same amount of time, all with the same filament. And you can really see the difference.
Yeah, you can. And is this down to, the artifacts are going to be down to vibrations?
There's a number of different things that can cause it. The ability of the extruder to output a particular amount of pushing force might have a factor. You've also then got things like eccentricities in the system, transmission errors in the driveline that will mean that as it flows, you don't get a consistent flow of filament, you get like a pulsing, and all that pulsing translates ultimately to the surface quality of the model.
Massively noticeable as well.
One of the biggest customer service tickets we get for Hemera is people who've either under or over tightened the idler tension.
No comment.
No
okay.
comment.
Yep,
right?
yep.
So we wanted to design that out because it's an obstacle to new users, and also making filament changing a bit easier. So we've got this geometry on here where as you click it, it locks, that disengages the hob, so you can now pull your filament in or load new filament, and then you simply pinch it and it relocks together, and that's you. You can obviously use scripts and automatically load it if you want to, but if you want to do that manual change, it's there for you to use.
So we spoke a little while ago about this button that's on the side here. What's the purpose of that, or is that just there just for something that you could perhaps use?
So I think we've put it on there with a few ideas in mind as to how people might want to use it, but I think the community is probably going to come up with loads of really cool extra ideas that maybe we haven't even heard of yet. It functions like an end stop. So you can wire it into your control board like an end stop, and anything that would run off an end stop trigger, like, okay, now I'm going to preheat my nozzle, or now I'm going to preheat my bed, or now I'm going to unload my filament and allow me to change for a new one. Anything like that. Sure, there's loads more sort of applications for that we haven't thought of yet.
Yeah. So what are these boards here?
So these are two products that we're really excited about, which we've co-developed with LDO and with Duet 3D. So these are specific toolboards that are designed to work and be implemented with Roto. So they each have the mounting points to work with Roto. So then on each of them, they're designed to take a signal from the main board. So for the Duet one, it's CAN, for example. Both of them have got inbuilt accelerometers on them, so once you've got everything mounted, not only is your wiring a lot more simplified, but you can run like your input shaping calculations with something that's actually going to remain on the print head. A lot of the time you'll attach an accelerometer to the print head and then you have to take it back off again.
Lose it.
None of that's needed here. The communication by like CAN or USB over from the main board.
Guys, thank you so much.
Thank you.
Great to see you both. We'll see you soon. Take care. Thank you. E3D has mass optimized Roto to make it as lightweight as possible. Users can now take advantage of this, of hitting the high motion speeds needed while pushing maximum flow rates at smaller nozzle sizes. E3D put a big focus on usability, incorporating features like the locking idler arm and optional sensor upgrades to improve the user experience. So that's the E3D Roto. Let me know what you guys think of this product in the comments below, and visit e3d-online.com to buy yours today.